So let us now create the LSTM cell. And so, as we said earlier, the cell starts with first state in H and C as an input. And we want to call this cell in the forward part. And in the cell, the LSTM is calculating all those values for all the activation functions and all the gates for every time step t, and then returns all those matrices with these corresponding values. And it will do this for every epoch in the forward part. So we have our cell, which performs the calculation for every time step recursively. And then it also creates some output that we also want to store in our LSTM. And also, as I said earlier, we don't need all of the output. It's just for keeping track of all the different states and all the different values for the different gates. So we have to, first of all, set up this cell. And therefore, we want to define a new method. That's the LSTM cell with all the input arguments. And in this cell, we perform the actual calculation. So for every time step in X, we first of all extract the value xt, and then we pass the value onto the forget gate. So it's start with the forget gate, and remember this is the equation that I show here. So we multiply all these values like xt with the learnable uf, we multiply ht minus 1 with the learnable wf, and we add the bias and then pass it on to sigmoid. So we will use np dot, of course, and then we pass it on. So it creates an output, and then we pass it on to the sigmoid. And of course, we want to have a value for every time step. And remember, we need to keep this value for every time step t for the backpropagation part. That was the idea where we have these different instances. So we do this for the forget gate and also for the input gate. And we also do this for the output gate and then also for z tilde. And then after that, we combine the information from the forget gate and from the input gate with z tilde. And remember, this here was element-wise multiplication, so we used np multiply instead of np dot. And then we have the combination from the forget and the input gate, and we pass this on to tangents hyperbolicus, and this creates the state ht. And also here we have to use element-wise multiplication. That's why we have np multiply and not np dot. And then we have ht, ct, and z tilde, and we want to store this in our lists. And of course, we want to store the output from the different gates in our corresponding matrices for the different gates. Because as I said, we want to keep track of those values. And therefore, we also want to return that. So that's the structure of the cell. And therefore, let's start with creating the cell and then call the cell in our forward part. And then we can run the first tests. So therefore, let me just move to our code. And we now, first of all, want to create our cell and then call the cell in the forward part. So we will call the cell in this forward part here, but first let's create our cell. So we just call it LSTM cell. And we need lots of input. So of course we need the data xt. So let me just also make some space here. Then we also need the initial values for the states ht and ct. Then we need all the activation functions. So let's start with the forget gate, with the input gate, with the output gate, then also with the different tangents, hyperbolicus, so tangent 1 and 2, hyperbolic k probably is the plural, and then you want to continue with the different lists for the different states. Oops. And the matrices containing the information from all the gates. Okay, and now we just have to follow the math. So we just take our xt and we use the command enumerate because we want to iterate over xt, which gives us the current value xt. But we also want to have the current index t, which corresponds to the time step. So we want to reshape it just to make sure that it has the right shape and that everything goes right when we use np dot. And now let's start with the forget gate. So maybe I should write this down. So let's start with the forget gate. So we create an output and we want to call it outf for forget gate. And we just multiply with np dot. So we multiply the learnables uf xt, and we also multiply the learnable wf, so which we have self wf with ht, and then we also add the bias. So we just have these values defined earlier. So these are all the learnables. So that creates, first of all, an output, and we put this output into the forward part of the sigmoid activation function. And of course, we want to do this for every time step. So that we store the information from the input for the backpropagation when we need that. And that creates ft, so the value from the forget gate, and we create this output by just calling the output. So just to remind you on the structure of the sigmoid, so we have a matrix, we enter that matrix, then it calculates the sigmoid, provides it as an output, and we also need it as the inputs then for calculating the derivative when we have backpropagation. And since the input is different at every time step, then of course the derivative will also have a different value at every time step. And again, that's the reason why we have these different instances t that we have defined here. So that's the output gate. And now let's do the same thing for the input gate. So also here, just want to be lazy, just copy and paste. But of course, we have to make sure that it all is correct. So it's the same structure. The only difference is that the learnables have the extension I. And also we have to take the correct sigmoid, because otherwise we're just overriding the previous value. And we also want to do the same thing for the output gate. So also here, we just copy and paste. And everything that's an F here is an O. Just make sure that you don't forget any of those. And of course, there are ways to do this in a simpler way because they maintain the same structure. So we could actually set up another class with a method that just performs only this calculation, and then we just call this method that we can make it. Well, then the code will be a bit more compact, but I really want to show it explicitly and want to leave away those things that you really see how it works step by step. And then, of course, later you can always optimize the code, of course. So that's an OT. Okay, so we have FT from sigmoid F. We have the output here. OT with O. All right, so there's no typo, that should work. But we're gonna test this, of course. So now there's the part with the C tilde. Yeah, let's just call it C tilde. Here the structure is a bit different. So we create the output for C tilde. Let's call it CT tilde, just to be clear. And then we have our NP dot. Then we use UG and multiply this with XT plus NP dot. We can actually copy and paste this part here. And we did do this with WG and BG as well. So now we call the first tangents hyperbolicus. So we just say tangents hyperbolicus 1, and then for the time t, and we just call the forward part where we just put in the output from the tilde. And then of course we create CT tilde itself. By calling the output from the tangents hyperbolicus, so the corresponding time t, of course. And now we call the output. All right, so we have the same structure here. We have G here, we have NP dot. It creates the output and we put it into the tangents hyperbolicus. And that creates the output. And now we can calculate the CT. And this is the part where we combine the information from the input gate with the information from the forget gate. And that's the element-wise multiplication. So we use NP multiply. So we're multiplying FT with CT. Now you might ask, well, where does it actually come from? So the CT comes from here, from the initial value that we have to provide here than earlier when we call the cell. So this is the CT. And from our CT, we calculate a new value CT. So this is the CT from the previous value, from the previous time step, and calculates a new one. So I can quickly go to the PowerPoint to show you what I mean. So that's the element-wise multiplication, and this part is FT multiplying with the old CT, and then we multiply IT with C tilde T. So we add this part. All right, so then we just say NP multiply the element-wise multiplication, which is IT times CT tilde. And then finally, we have to take this information and turn it into, and put it into the next tangents hyperbolicus. So we just call the next tangents hyperbolicus at time points t. Then we have our forward part where we just feed in CT, and that creates HT. So HT, then NP multiply. And then we have the output from the tangents hyperbolicus 2. And we have OT. What's this? What's the output from the output gate? So then we have the new value HT. And then we can save it. So we can just save HT at t+1, because that's the next step. And then we have C t+1 dt, and we have C tilde. All right, so we have all the different states. And remember, here's our input, where we have the different activation functions, and we have the different lists where we have values for different states, but we also want to save the output or the numbers generated from different gates, like forget output and the input gate. So we also wanna add this. So we have the forget gate, which is here. We have the output gate, and we have the input gate. And also remember, we have HT as input, and we use HT for calculating the numbers for the different gates. But then we overwrite HT again, and we save the new value here. And the same way we do with CT, and we start with the initial value that is an input for the cell. And that's why we are always one time step ahead. And that makes sense because we also have enough space in our list, so we will not have any error message. So, and then we want to return those values. So we just return those values now. So we want to return H, C, then those different activation functions. And of course, we want to return all the values here that we have here as well. All right, so that's our cell. And now we need to call the cell in our forward part. And then let's hope there's no typo. And if there's a typo, of course, we're gonna fix it live so that you can also see what happens if there's a typo, error message. How can we solve it? Because if you do this, again, usually you have 1 or 2 error messages. But let's see whether we get lucky. So this is the output. This is the input. So the only thing we have to do now is to call our cell in our forward method. So we have our forward method here already. So we just only need to add one particular line that we just say self. And then we call our LSTM cell. And it's been recognized already. Then we can just leave it as it is. Of course, we have to add a few modifications. So what do we need as an input? First of all, we need the initial value of HT, which is the value that we have in H0. And we need the initial value for CT as well. So we have HT, we have CT, we have all the activation functions. So let me maybe just add a line break here. Then we need to call all these matrices as an input. And these matrices are saved here or have been generated during the init. So we just add self. So we add the self for this, for this, for this, for the different gates, and also for C tilde. So the error message disappeared. So the syntax is correct, but there's still something we need, and this is the output. So we want to generate this output here. So we can just copy and paste this. And then just generate this output. So it looks very, yeah, let's say a bit convoluted. But yeah, that's the idea, that we keep track of all the different states and that we also keep track of the values in the gates. And we want to create some plots. Okay, so maybe I should also add a comment here calling the LSTM cell. And of course, once we convinced ourselves that everything works, then you can remove those parts we don't need for running the actual LSTM. All right, so let's test it and let's see whether we get something that kind of makes sense. So we want to, first of all, compile it, and then we want to test this in our cell. So remember, this is our data set. And I want to say a few more words about the data set before we run the test. So we want to do the following. So this is again our data set where we have a short-term periodic behavior, which is represented by the sinus. Then we also add noise. And then we also have a gradual change over a longer time span. And we want to see how the LSTM deals with both the long-term and the short-term change. And in the lecture of the RNN, we had pretty straightforward predictions, so that we just had the X value and we wanted to predict the Y value, which kind of, so the training worked, but the output was not really satisfying. And we want to do the same thing with our LSTM as well. However, how it's actually done is in a slightly different way. So what you actually want to predict is YT in the future. And let's say you want to predict YT in the future, let's say DT. So we can also train YT as an input, and YT plus a shift DT is our training data. So that we learn, given we have a certain time point, what will be the behavior of our data set in the future. And we want to try both ways. So we want to, first of all, try the prediction from XT to YT. But again, we want to know what YT is in the future. So therefore, we also want to try the other prediction or the other way how to do that. So we're starting with YT as our XT, but the training is YT in the future, and then we hopefully can make some predictions in the future. So we now want to run this code, and we will also want to create a few plots. So we want to call our LSTM. Then remember the init needs the number of neurons, and in the forward part, we need XT as an input. And then it should actually create all those values for the different states. And we would just want to plot those values. For example, let's say for the first 20 time steps, but all the neurons. And let's see what we're going to have. For the RNN, we had kind of zigzag pattern between different states, +1 and -1, because we pass it on to a tangents hyperbolicus, and it maps or compactifies the values from -infinity to +infinity to -1, +1. So we should kind of see roughly the same pattern, but it's a bit different because we also have the other layers now in between, or the other activation function. So we should see a similar pattern, but not exactly the same pattern. And let's take a look now at these patterns. So let's go back to our code, and we have our data here, and now we want to call our LSTM. So we just say, let me just some space here. So that's our data. And then we just say from LSTM. And we would just want to import everything. And so let's do that, and let's call it first of all. And then we want to call an instance of the LSTM, which is then LSTM. And number of neurons is the input, which is 200. So let's also check whether we have in our LSTM. So that's the init. And we have the number of neurons. So let's see whether that works or whether we get an error message. So let me just check whether I saved it correctly. Right. Okay. So let's check it again. Would be in the right folder. Ah, sorry. That's of course there's an equal. Okay. Of course that doesn't make sense. So well, that can happen. Okay, so no error message. But yeah, always check twice. And now we should have the forward part. Let's see whether it recognizes the forward part. It does. Then we have xt as an input. And now it should do the math and create all these values. And let's see whether we get an error message now. We don't get an error message. It's still, there might be things that are wrong. Let's create a plot. And we should see this kind of zigzag pattern, but actually not exactly as before. So the peaks should have different heights, and we should have also different values for the different neurons. So let's create a plot for H in LSTM. That was too fast. LSTM H. And we actually should see that. So for example, if we just go to LSTM and use the autocomplete, we should see all the functions and all the attributes. There's another thing what you could actually do. You can just list all the attributes with the dir command, and then you have a list of all the attributes, and of course you can filter for those attributes in a loop. And for example, you can then of course avoid all the dunder operators with the so with the double symbol here. So you can of course exclude them by running over a loop, and then you can extract all the attributes that you need. So, but we have all the attributes, so that looks good. So they're all being recognized. And then we just create a plot. And we want to just look at the first 20 values of all the neurons. So we have NP arrange. And also that you understand the structure again, so that H is a list. Let me just call it again. And let's show this explicitly. So H is a list. And it has as many entries as time points. In our case, it's 801, because that's also the length of xt and yt. But remember, we start with an initial value, so I have one more entry. And then for every time step, we have 200 states. And now we want to just take a look at the first 20 time steps. So we just say we have H and the first 20. And we will have 200 neurons. So we want to create a plot with an alpha that we see the different lines. Okay, so let's create a plot and let's see what we get. And that's the plot. And of course, we can't really tell whether it makes sense now, right? But it's just the correct structure that we see. So the particular value itself, of course, you can't really tell now. But if you see a structure that looks like this, you're at least not so far off. And it's also for checking error messages. So, but that kind of looks good. So that's what you should also see. So let me expand this a bit. And you can also do this for all the other states. So let me just do this for the, so we had this for C, but we can also take a look at the forget gate, for example. Take a look here. And then we should have similar patterns. So they all more or less kind of look alike. So if you don't get an error message, and if your plot looks like that, of course that's not a proof that every single value is correct, but at least you're not so far off. So we just plotted those things, and again, that's what you get. And essentially you see those different functions at work, these activation functions for, so if you plot something that passes the tangents hyperbolicus, for example, those values should go from -1 to +1, so like this here. And for the sigmoid, from 0 to +1. So for example, the gates, they should look like this. So if you, for example, have to forget gate or something. Okay. So then we have our forward part. And now we have to implement the whole backpropagation, and we want to start with the backpropagation through time. And I want to explain this step by step in the next chapter.